Here we go, even more fun with factoring. The goal for today is to factor polynomials that are the sum or difference of two cubes. Okay, what do I mean by a perfect cube? Can you give me an example of a number that's a perfect cube? 27. What were you going to say? 8. Those are both perfect cubes. Okay, let's list as many as we can. So 1 cubed is 1. So 1 is a perfect cube. Okay, 2 cubed. What's 2 cubed? 2 times 2 is 4 times 2 is 8. 8 is a perfect cube. Okay, 3 cubed. 27. 4 cubed. That's a little harder. 64. 5 cubed. 125. That's getting harder now. 6 cubed. 216. 7 cubed. Does anybody know 7 cubed? I don't know either. I don't know either. What is it? 343. Okay. I would have said that, but I wouldn't have been sure. Okay. Really, you just need to know through 5 cubed, and you'll be good to go. There's ways to check if something's a perfect cube. We'll talk about that later on. So these are the first 7 perfect cubes. So what do I mean when I say the goal is to factor polynomials that are the sum or difference of two cubes? Well, we've got a couple of formulas, just like we had for the difference of two squares formula. We've got a formula for both the sum of two cubes and the difference of two cubes. So it turns out that a cubed plus b cubed factors. And it turns out that it factors to be the quantity a plus b times the quantity a squared, okay, minus ab plus b squared. And then the difference of two, so that's the sum of two cubes formula, and there is one for the difference as well. It looks largely the same. You just have to switch the minus and the plus, a certain minus and a certain plus around. So if you have something of the form a cubed minus b cubed, it factors to be, okay, the first factor becomes a minus b. The second factor becomes a squared plus ab plus b squared. But if you can remember the first one, you can remember the second one. Okay, at this point, some of the formulas start to look similar, right? So it would be a good idea to make flashcards. So what do I mean by a flashcard? Well, get like a 3x5 card. They're not expensive. Go to a dollar store. I bet you can get some for $1. 99 cents maybe. And on one side of the flashcard, put a cubed minus b cubed. On the other side of the flashcard, put the right-hand side of the formula. Just look at it before you go to sleep at night. You'll have them memorized, and you won't even know you did it. By the morning, your brain will know it better than it did the night before. It's weird. Something's happening while you're sleeping and dreaming. It's really putting your memories, what you're thinking about currently into the long-term memory, perhaps if you study it before you go to bed. So give that a shot. Also, write down the formula every time you use it. That'll help you memorize it. Okay, how would you verify these formulas? You multiply, right? It's the same way you check your answers when you're done factoring, right? Let's prove the first one. The second one will be similar. Proof. Now I'll take the right-hand side, a plus b times a squared minus ab plus b squared. I'll multiply it out, and I better get the left-hand side, and then that'll prove the formula. Okay, well, that's just good old distribution, right? You have to distribute this a right here, to every term in the second polynomial, and then distribute the b to every term in the second polynomial, and then add like terms together. So let's distribute the a. What do we get? If we distribute the a, what do we get? Yeah, so this guy goes up, this exponent right here goes up by 1, so a cubed minus, distribute it to the minus ab, what do you get? A squared b. Distribute it to the b squared, what do you get? Plus, because we're just distributing over addition, plus a b squared. Does everybody agree that's what we get when we distribute the a? What about when we distribute the b? This b right here to every term in the second polynomial. What do we get? So it would be, think of it like distributing this a squared to this plus b, and you'd get plus a squared b, wouldn't you? Which we could line up right here, plus a squared b, right underneath its like term. So that's what you get when you distribute b to a squared, or a squared over a plus b. Okay, now distribute the b over a minus ab. What do you get? Minus ab squared. I can put that result right underneath its like term. And now distribute the b to the b squared, the plus b squared. What do you get? Plus okay, we're distributing this guy to that guy. Yeah, well, that's okay. You were shouldering the load for the entire class, and then when they were counting on you. So what do you get when you distribute b to b squared? B cubed. And no like term to line it up with. Add vertically, what happens all there in the middle? Minus a squared b plus a squared b. They cancel out. These guys cancel out too, and what are you left with? Exactly what you're supposed to be left with, the original, what was originally the left-hand side of the formula, right? So that's it. That's the proof. You just proved it. Or if you looked at that, you just looked at a proof of it. Could you do that yourself? You could. If you can multiply, you can do that. If you can multiply polynomials, you could prove it. By the way, then if you forget exactly what the formula is on a test, but you're good at multiplying, could you write what you think it is and check it really quick? So this isn't just something you'll never use. If you're smart, you'll use it because your memory's not perfect, and you can check your memory by multiplying this formula out and making sure it's correct. Okay, now the technique on factoring these things is much like what we did last time with the difference of two squares and the perfect square trinomial factoring formula. You have to identify what's acting like a from the formula, what's acting like b, and then plug and check. So I would say most of the battle is identifying what's acting like a and b, and then, of course, being able to write down the formula in the first place. So the directions are obviously to factor. First example, x cubed minus 27. It looks like the difference of two perfect cubes. So which of the two formulas are we going to use here? The first one or the second one? So hopefully it's clear. It's the difference of two perfect cubes in the first example. Write the formula down. So every time you use it, if you write it down, you'll have it memorized in no time. A cubed minus b cubed is equal to a minus b times the quantity a squared. Here's a good way to remember it. When it's minus right here, it's going to be plus right here. So a squared plus ab, not 2ab, that's from another formula. Just ab plus b squared. A lot of students like to put a plus 2ab here, but that's from another formula, the perfect square trinomial factoring formula, right? And then close that parenthesis. Okay, so what's acting like a here? What are you cubing to get x? What are you cubing to get x cubed, I should have said, sorry. X. So another way of thinking about that is what is the cubed root of x cubed? It's x, right? Okay, what are you cubing to get 27? Well, that's b then. B is 3. And then you just plug in to the right-hand side of this formula so that this guy, x cubed minus 27, factors to b. You guys tell me, what's a minus b in this case? X minus 3. That's the first part, the a minus b. Then what's a squared? X squared. What's plus a times b? 3 times x. Plus 3 times x, and then plus b squared? Plus 3 squared, which is 9. Okay? Now, you're tempted to try and factor that trinomial, aren't you? X squared plus 3x plus 9? That thing's not going to factor. It's just not going to happen. Okay. So that's our first one. And you could always check it by multiplying it back out if you wanted to.